As of now, we spoke about objects undergoing simple harmonic motion. So let's recall what simple harmonic motion is. If we have a spring, we take a mass, attach it to our spring, we stretch that spring and let go, the object will begin to oscillate back and forth. And the oscillations will continue to be cyclical. So that simply means the amplitude of our oscillation in simple harmonic motion remains constant. And that's because the total energy of our system remains constant. Now, a real oscillating system will over time experience a decrease in amplitude as a result of internal friction and air resistance. So in other words, when we spoke about simple harmonic motion, which is essentially an idealized type of harmonic motion, we neglected the air resistance and frictional forces. But these forces do in fact exist. And in a real oscillating system, these forces will decrease the amplitude of the oscillation over time. And over time, if I take the mass, I stretch and I let go, the object will eventually come to a complete rest. And that's because some of that kinetic energy and elastic potential energy is transformed into thermal energy of the spring and the mass, as well as the thermal energy of the molecules surrounding our object. So, the amplitude decreases because the energy goes into thermal energy. It's transformed into thermal energy of our system, of the mass as well as the spring. And if we graph our motion of the object, where our y-axis is our displacement and the x-axis is the time, we'll see the following diagram. So notice initially when I stretch my object to a maximum displacement, to my amplitude at time equals 0, the object is found in this position. But eventually over time the amplitude will decrease, shown by this dashed line, and eventually the object will come to a complete rest. So this type of realistic harmonic motion is known as damped harmonic motion. So in real situations, any object that is vibrating or oscillating back and forth is experiencing damped harmonic motion. So why in the world do we talk about simple harmonic motion? Well, simple harmonic motion is much easier to deal with mathematically. And in fact, we can use in some instances simple harmonic motion to approximate damped harmonic motion. So, let's talk about something called the damping force. The damping force is the force that acts on our object to impede the oscillations of the object. So the damping force creates the damped harmonic motion. So the damping force is equal to the negative of our B times V, where B is simply our proportionality constant and V is the velocity of the oscillation of the object. So we see that if the oscillation velocity of our object increases, the damping force also increases. So let's recall the second law of motion and let's try to derive an equation of motion for the following object undergoing damped harmonic motion. So, recall according to Newton's second law of motion, the net force acting on the object is equal to the product of the mass of the object and its instantaneous acceleration. Now, recall that we have two forces acting on this object that is oscillating, that is attached to the following spring. One force is our damping force given by this product, and the second force is the restoring force created by this spring, and it's given by Hooke's law. So we have negative k times x, where x is our displacement, k is our stiffness constant, and a negative simply means that our force acts in the opposite direction of motion. Minus b times v. Once again, the negative simply means that the force acts in the opposite direction of motion. So we have negative k times x plus negative b times v is equal to m times a, according to Newton's second law of motion. Now let's bring these two negative terms to the right side. So when we bring them to the right side, they become positive, and we have the sum of the following three products. So the sum of m times a, where m is the mass of the object, a is the instantaneous acceleration, plus k times x, where k is the stiffness constant, x is our displacement, plus b times v, where b is our proportionality constant, and v is the velocity of the object. So let's suppose that I want my equation to only include the position, so the displacement, because we're looking for the equation of motion for objects that are undergoing damped harmonic motion. So that means we have to replace our instantaneous acceleration with the second derivative of our position function with respect to time. So another way that we can write a is by using this quantity. Now, in the same exact way, by definition, velocity is equal to the first derivative of our position function with respect to time. So we can replace velocity with the following first derivative. And that means we have the following equation that only has displacement terms. And so this equation is known as the equation of motion for objects undergoing damped harmonic motion. Now, does a solution to this equation exist? If a solution exists, that means that solution is the position function of our object with respect to time. So we want to find what that solution is. So let's make an educated guess, and let's suppose that our solution is given by the following general formula. So x of t, where x is our displacement and t is our time, is equal to a, our maximum displacement, our amplitude, multiplied by e to the negative gamma times t, multiplied by cosine of omega prime multiplied by t. Now, we make the assumption that at time equals 0 seconds, our displacement is our amplitude. So at time equals 0, our object is at its maximum displacement. So that means our phi term inside this term goes to 0. Now, also notice that this omega prime, our angular frequency of the object undergoing damped harmonic motion, is not the same angular frequency that objects undergoing simple harmonic motion experience. So our omega prime is not equal to our omega, which is not equal to the square root of k divided by m. So let's actually skip all the calculus. So what we actually want to do is we want to take the first derivative of this solution and plug it into this quantity. We want to take the second derivative, plug it into this quantity, and then find the conditions under which that solution works. And the conditions under which that solution work are given by the following two equations. So this general formula is a solution to this equation of motion for objects experiencing damped harmonic motion only if our omega prime, our angular frequency for damped harmonic motion, is equal to the square root of k divided by m minus b squared divided by 4m squared. And also the following solution, the following condition must hold. Our gamma must equal to b divided by 2m. If these two conditions are held, then this becomes a solution to this equation. And in fact, we can use these two equations and this general solution for objects experiencing damped harmonic motion. So if we take this quantity and plug it into this gamma, we get the following general formula for our position function for a lightly damped harmonic oscillating object. So we have x of t is equal to our amplitude multiplied by e to the negative bt divided by 2m, where this e to the negative this term is simply this exponential function here as drawn by this dashed line, multiplied by cosine of omega prime multiplied by t, where omega prime is simply this formula. Now, let's try to find what the frequency is of our object undergoing damped harmonic motion. Well, recall that our angular frequency omega is equal to 2 pi times the frequency. So we have omega prime is equal to 2 pi times the frequency prime. If we take this entire term and plug it into this omega term, we get that the frequency of our object experiencing damped harmonic motion is equal to 1 divided by 2 pi multiplied by the square root of k divided by m minus b squared divided by 4m squared. Now, what this equation basically tells us is the following. The frequency of an object undergoing damped harmonic motion is smaller than the frequency of the corresponding object when that object is experiencing simple harmonic motion. And that's because for objects experiencing simple harmonic motion, we don't have this term. So if B is 0, then that means we don't have a damping force, and our frequency is simply equal to 1 divided by 2 pi times the square root of k divided by m, which is the equation for frequency of objects undergoing simple harmonic motion. Now, how else is this equation useful? Well, it's useful because it can give us what type of damping our object experiences. So let's suppose we take this entire term. So we have k divided by m minus b squared divided by 4m squared. So we took the inside. Notice the inside cannot be a negative number. If the inside is a negative number, that means that this inside radical will be negative, and so the radical of a negative is imaginary, and so we can't have that. So k divided by m minus b squared divided by 4m squared. Now, if these two quantities are equal, then this entire term becomes 0. So if b squared equal 4mk, that means k divided by m minus b squared divided by 4m squared will be 0. And if this term goes to 0, that means the entire frequency becomes 0, and that implies that the object will come to equilibrium. It will come to a complete stop. The frequency will go to 0. Now, from this result, we have the following 3 important concepts. We have something called overdamped, underdamped, and critically damped harmonic motion. So when an object is experiencing overdamped, what that basically means is that the b squared term is much larger than the 4mk term. And what that implies is an object that is experiencing overdamped harmonic motion, well, the object will take a very long time to achieve its equilibrium position. It will take a very long time to actually stop oscillating. When an object is underdamped, that means that b squared is smaller than 4mk. And this means that the object will oscillate several times before actually coming to rest. And we also have something called critical damped, and when an object is experiencing critical damped harmonic motion, that means that b squared is equal to 4mk. And if b squared is equal to 4mk, this term is 0, and that implies that the object that is experiencing critical damped motion will take the shortest amount of time to come to equilibrium, to come to rest.